Cool. I hope everyone can see the paper. The paper I'm presenting today is called Data Shapley in One Training Run. And it's an honorable mention in this year's ICLR 2025, which finished last week. And the paper is about, so the overarching problem that the paper is trying to address is how can we figure out the contribution of a data point in a data set to the performance of a model that's been trained. So, and in that way, you could figure out like maybe 80% of the performance is coming from like 20% of the training data. This paper specifically is actually focused on a subset of this problem, which is that there's a lot of methods based on like Shapley scores that solve this problem in one way or another, but they're all very computationally expensive. And what that means is that we can't really apply them to the really large models that we're using today. So this method, it proposes a way of calculating Shapley scores that, and consequently figuring out the contribution of data such that you could, in theory, train a really large language model and calculate the Shapley scores of your training corpus. I think it would be really cool if I don't know, like OpenAI was willing to shell out $5 million to train a GPT-4 again with this to see what we would find out about the training corpus. Because the training corpus that they're using for pre-training, I'm betting is pretty similar to like what's online, like the red pajama data set that you can find in Hugging Face. So it'd be cool. Maybe if we could even do like red pajama if we could get, someone could get sponsored to train a model that way. Anyway, first, before before going into the paper, I just wanted to highlight some of the use cases for this, which is like calculating the contribution of data at scale. They say the lack of reliable data attribution mechanisms can lead to significant legal and societal issues, resulting in growing backlash against the broader use of data in model training. So this has to do with like using other people's data without their permission, or not being able to understand how important one source of data is, and that can create these kinds of issues. And then the other one, which is, moreover, foundation models are often trained on massive data sets straight from the internet, which can include low quality and harmful content. So another use case of this is like removing data from your data set, which actually isn't useful in the downstream tasks that you want to use this for. And they actually show a case where they filter out data and get a more efficient model, data efficient training method. Okay. Let's see. So those are some of the use cases of where you could use it. And the basis of this method is calculating Shapley scores for each data point in your training set. What I think is really interesting, as just like some background, is that Shapley scores actually weren't intended for this use case. The original use case for this method was, say you have a game that you're playing with a large number of people, or more than 2 people, and you have 5 people who are cooperating with each other to maximize their performance in the game. And together they get like 20 points. How could you fairly distribute those points between those 5 people based on their contribution? And the Shapley score is something that does that. So it says, these are the 3 properties of the Shapley score over here that I've highlighted in these different colors. 1, it assigns equal scores to equally impactful data points. So going back to this case where we're talking about data points, ensuring fairness. So we know that it's provably true. it's provably true that it assigns scores fairly. The second is that the sum of the total contributions equals the total utility. And what that means is that the scores are interpretable because you know, like it's a percentage of the total utility of the score that you give to a data point is a component of the total utility you get from your whole data set. So you could literally divide by the utility of the whole data set to get your percent contribution, sorry, of that data point. And lastly, it supports additive decomposition across multiple utility functions, allowing for the calculations of attributions to the entire data set. We'll get onto this one later, what that means, because I feel like it's not an easy one to explain, but when you see the equation, you understand it. Okay, so that's like kind of a background on Shapley. The whole idea is we get these fair scores for the contribution of each data point in a data set to the model's performance at the end. Okay. So let's see, what do I want to say around here? That's good. I won't go through this because we're going to go through this later. So I'll just jump into. So we talked a little bit about the Shapley score, and here's in this section they give you a more like mathematical framework for it. So let me just zoom in a little bit. So I'm talking about. So this is kind of like a problem formulation. You have a data set D, your training data set, with each data point being Zi, and there's big N number of data points. Calculating the Shapley score means you calculate a score which is called phi Zi. There's N points. It's called a score vector because you have like N of these different scalar scores, where each of these scores is a Shapley value at that point based on some utility function. So let me just get some. Now, when you're calculating the Shapley score, it's always with respect to a utility function. And that's like the downstream task that you want the model to perform well on, or some set of tasks that you want the model to perform well on. Now, the one that they point out that's used often in the context of the models that they're talking about is performance on a held out validation set. So your utility function is you train on some training set, which is S here, and then it's your performance on a held out validation set. And that's the utility function that they use throughout. So the utility used to calculate the Shapley score is the performance on a validation set. We'll go into that a little bit later. And then over here in definition 1 is where they define the Shapley score of a data point. Now, I wanted to go over this quickly because I had to look at it maybe like 4 or 5 times before I feel like I really understood what's going on. And the reason why I want to show it to you is because I wanted to highlight how computationally inefficient calculating the Shapley score is in my mind. So if you look at the equation here in definition 1, you have 2 sums. The outer sum is going over like from 1 to n, so the size of from 1 to the size of the data set, and it's actually iterating over different possible sized subsets. So you could have a data set of size 1, or a data set of size 2, or a data set of size 3, subset of size 3 of your training set. And then the inner loop is iterating over every possible subset of that size that does not include like with or without the data point that you're looking at. So if you had like, I didn't do the calculation now, but I think if you do like 10, if you have 10 data points in your data set, then this already becomes like I don't know, like 500 different, like the number of things you have to calculate is of the size 500 or something like that. You have like 1,000, it's probably like billions. So it's actually pretty inefficient to calculate this original score. But the great thing about it is that it has these properties that we talked about before, like the fairness attribution. And also one other one that they talk about here is that if your score is truly a Shapley score, so if it's the one that you see here that meets the criteria in definition 1, then you can calculate the Shapley score of like a linear combination of 2 utility functions by calculating their individual Shapley scores and then multiplying by their scalar multiples. And this definition is a really important definition for this paper. This ability to go from here to here. So yeah, just wanted to talk a little bit about what the Shapley score definition is. My opinion, it's crazy. But then they also mention a lot, probably the most common existing method for calculating Shapley scores in this context of deep learning models with large data sets and how you could do that. And they call this retraining-based data Shapley, which is where you train the data set on multiple different subsets. You train a model on multiple different subsets of the training set, and you use those results to approximate the data Shapley score of the model. And that's called retraining-based data Shapley. And one thing is, like, it's very it takes a lot of computation because you have to do many, many training runs. And consequently, it's not efficient. Another issue with it is that and they say this in the previous page, but I figured I'd mention it here. With this method is that it doesn't tell you the attribution of data for a specific data point. I mean, for a specific model, it tells you for like a specific training method, because whenever you initialize a model, there's a lot of hyperparameters you might choose, or and some you don't even choose. It might just be like the randomly initialized weights of the model, which is something that you can't really choose. And so it doesn't give you an exact Shapley score for that trained model that you have. It just gives you one for the overall model class and method you're using. And the last one is that the scores can be highly unstable. So you might get like very different, that means like you might get very different scores if you did it once versus another time. So it's not really that easy to calculate useful scores with it. So there's a lot of shortcomings of the retraining-based data Shapley method. The good thing is that it is gives you Shapley scores, and so you can do good, proper data attribution with it. But so that's why the whole paper is about their method, which they call in-run data Shapley, which is where you only have to train the model once in order to calculate the attribution of data, so how important each data point is to the model's performance. Okay. They use the same utility function that we were talking about before, which is performance on a validation set, just so you guys know. And so the first thing that they do to break this problem down a little bit and make it a bit easier, is they calculate, they instead of calculating the utility score of the entire training process, they calculate the utility score of each training step. So when you train a model with stochastic gradient descent, you randomly select batches and you calculate utility of each training step of data points. And the whole idea is that, as we'll see below, but I'll just remind you of it again, using this property here, since the training method is composed of training steps and we're calculating the utility function for each training step, we can calculate the utility function of the entire training method and use the the Shapley scores for individual steps to calculate the Shapley score of a data point for the entire training method. Okay, so the first thing they do is they calculate say we only need to calculate the utility scores and Shapley scores for individual updates one at a time. And that's why you see their utility score is what they have. So first off, let's go through equation one. S is the training set. And so their utility function for an update is they have a data point from the validation set, and they calculate the loss of that data point minus before the update and after the update. So WT plus 1 is after the update, and WT is before the update, where the update to the model, so to the weights of the model. The update to the weights of the model is described by this equation here. It's what we all remember. Yeah, go ahead, Arvin.
So the S is technically the subset of the data set, right?
Sorry, you're right. It's a subset that's being used for that batch.
Exactly would effectively be batch index, yeah.
Mm-hmm.
What was the one thing that came to mind was don't we have to have this combinatorial factor in there as well if we want to do these calculations?
Yeah, to be honest, I didn't understand how they got over that, but
because I think if I remember correctly, when people use the Monte Carlo sampling, that they have to put like some combinatorial adjustment based on if we were to sample different sample set sizes. Now, I suppose because you always use the same size as here, if you leave your batch size constant, and by batching you just sample the members of the batch, essentially, that maybe because it becomes a constant factor, it just falls out of this. I don't know.
Yeah, I'm not sure. I think that this this section here, data Shapley for an entire, let's see. Yeah, I'm not sure, to be honest, how they get over the combinatorial factor, and that's just like how they have to sum over different subsets of the data in the original equation.
So yeah, it might be that this is already a form of Monte Carlo sampling that they do rather than, yeah.
Yeah, maybe that's it. I'm not sure.
Yes.
I think it would require. I'd probably need to read it again, but it's a really good question. Yeah, it's probably like if I were to implement this, I'd definitely have to figure that out. But anyway, let's go back to this. So ignoring that for now, but it shouldn't be ignored. It's just that I can't answer it. So the utility function is the difference in the validation loss of a single validation point before and after an update. And let's see, one thing that I found, because we were saying the performance on the utility function is a performance on a validation set, and then all of their methods are, all of their equations are for like a single validation point, but they say it's trivial to extend it to more than one validation point. But I was wondering in experiments and when they implemented it, if they were just using a single validation point or not. It wasn't super clear, but maybe I just didn't read it clearly enough. But anyway, so the first step is we decompose calculating the utility of the entire training over the entire training set, training period into individual steps, and then we can combine them back together later. That's what this equation here is that I highlighted in yellow. So U is the entire training period, and then UT is all the individual utility functions for each step. And then, yeah, something about over here is that they show, I think over here they're saying that like it doesn't matter that you're only using a batch of the data set. It's the exact same as if you were to use the entire, you could treat it as if you're that data point is part of the entire training set. So basically, the Shapley scores that you calculate on the batch are the Shapley scores, as if these data points were part of as if they're part of the larger data set. Yeah, I didn't go through that well, but I hope I hope you got some of it. Okay. So they've talked to us about how we calculate the utility function, and then the next thing is like how do you and some of the theory behind that, like how do you efficiently calculate the Shapley scores? Because that's what we want. That's the next section. So the approach that they take here is, instead of doing a Monte Carlo approximation where you like sample multiple different subsets or something like that, they use like a Taylor approximation or a Taylor expansion. And so if we look in this equation here, you can see the Taylor expansion of the utility function. So usually when you have like, if you look at a Taylor expansion, it's that this term is on the other side. This term would be over here. But since you're asking for the difference between the two, it's over here. And so then you get what you see here, which is, if you look at what it's saying, okay, the gradient of the weights when you input the validation point times the difference in the weights between the update after the update. That's the first order approximation. So if you just had this, it should be like relatively close. Well, not always, but like relatively close to the correct answer for the approximating utility function. And then you have like the second order term where you have your Hessian, which is like the second order, like the gradient. If you were to take the gradients twice with respect to the weights, and you get a matrix then. And then you have like this term here. So one thing that they point out is that the difference between the weights over here is actually equal to this term, which is the term that you update the weights by, which is your learning rate times the gradient of each of your individual points in your batch or your subset. So you can put those in here, and you can like fill those in here. And then if you do that, then you can get the two methods that they're suggesting. One is their first order in-run data Shapley, which is where you're just using this term to calculate the utility function, and you substitute in the gradients that you calculated, and you get this. So your Shapley score would be like your learning rate minus times your learning rate times the gradient of the weights with respect to the data set times the gradients with respect to the data point that you care about. Yeah. Something I want to say about that. So yeah, this is how you would calculate the Shapley score. Nothing else to say there. Okay. And then, yeah, go ahead, Arvin.
It is probably a stupid question, but does it sort of mean that every data point must have an individual loss assigned to it?
No, that's not a stupid question at all. In fact, that's the reason for the method on the next page, like that ghost dot product method, because
if you had, for example, a loss that actually is properly working on a batch where sort of if the batch size goes to 1 or so, the loss would become meaningless. It's probably quite a contrived argument, but then that technically would not be holding anymore, right? So if you were to optimize some sort of distribution, for example.
Yeah, I see what you're saying. But anyway, yeah, the answer is no. You like these equations require a loss per data point, but then in the end, and calculate, actually the computationally hard part is calculating the gradient of the weights with respect to each data point, because that's not something we actually do in all of the methods that we update models with, and that's why. And if we did do that, it would make things a lot slower.
Yeah. Cheers.
They also, I guess I won't mention that. It's not too important. Anyway, and then they have that this method where you're just using this first term and you're just substituting in this term is called first order in-run data Shapley, and we just talked about that. And then they have the second order, which is where you also take into account the second term with the Hessian, and they show you how they calculate that here, where you have like your learning rate squared divided by 2 times like the loss with respect to the data point in question times your Hessian with respect to the validation point times the sum over these individual points. I didn't actually see how. Oh no, I guess I understand how they got this. But one thing that they point out is that like the loss in most deep learning methods is like 1 to the like it's a small number, much smaller than 1, and so when you square it, it's going to get exponentially smaller. And so they say that like this is a good approximation, especially like ignoring the higher order terms because the loss is so high. Like in the third order approximation, you'd probably have an incredibly small number. So you might have you'd have an incredibly small number, so you don't need to take into account those terms. One thing that I thought was interesting, and I highlighted it here, is that if you look at this second term, when you're calculating the second order approximation using the Hessian, what you're doing is like you're taking the contribution expressed by the gradient of the point in question that you care about, and then you're weighting its contribution with respect to the other terms in the data set, I mean in your batch, in order to calculate its contribution. And they said that like an example where, because I found this kind of confusing. I was like, when would a data point be affected in that way by its other data points? Like when is its contribution less important? And they say an example would be like if there's multiple copies of the same data point in your batch, then you would have the case where you'd have a lower weight on the contribution of your data point that you're calculating the Shapley score for. So that's an example. I just thought that was interesting. Yeah. Okay.
Isn't this the answer to Arvid's question earlier? Because by doing this, aren't we getting the weight of each data point?
So you do still need to calculate the weight.
So we don't have the computational explosion because we've done this calculation. So we know the weight of each data point once we do this.
I think it was more the question of is this a sum of gradients or is it an actual chap value?
Mm.
And the answer could be probably. Yeah, I'm not sure.
Yeah. So that was just my thought. Just a question. Yeah. Sorry. Carry on.
Yeah, I'm not sure either. I wish I could answer that. But anyway, so you have these two methods where they're using the Taylor expansion to approximate the Shapley score, assuming the Shapley score is correct. First order in-run and second order in-run. But that's not enough because as they point out here, in order to calculate the Shapley score for each data point, you'd have to calculate the gradient of a weight, all the weights in the model with respect to each data point. So if you have a batch size of size BT of size 8, that means that you have to do, you have to process each data point individually, which makes the the training method like 8 times longer. So everything right now, okay, they've been able to like reduce the computational complexity a bit, first from like being completely impossible to being something like somewhat tractable, and now it's still like, but no one would ever use this, especially with foundation models, because you'd still like increase the training time by like a factor of whatever your batch size is. So that's too much. So then what they do is they introduce a technique that's been developed in differential privacy, which is actually, I don't even know what that is. I guess it's like somehow you differentiate the model to calculate how private something is. I don't know. But anyway, if anyone knows, feel free to interrupt and tell me. There's a method in there called ghost clipping, and they take inspiration from it to propose something they call ghost.product. And the short of it is, if you go through the math, you can do some like intelligent substitutions. And I think the main one is like these last 2 terms here. And the key point is, if you look at these last 2 terms, L to Li is like the loss with respect to a data point I, and L is the loss with respect to the sum of all the, like over all the data points. And they show that these 2 are equal to each other in this math over here, in the simplified math. I'm sure it gets more complicated as you keep going down and like actually adding the complexity of these models in. But the short is that like they figure out a way to take only things that are already calculated when you do a backward pass, in order to calculate the Shapley score for each individual weight. That's the whole idea, by doing this ghost.product thing. Yeah, I'm not going to go too far into it, because I think that if you want to go far into it, it's there's a lot of depth that if you go there. Yeah,
differential privacy is used during federated learning. It's if I do not want to expose my, say, medical data to for other people to see, it's a way of using my data in the model, training on it, without having that information leak. And there are certain techniques that they use in their clipping and so forth.
Thanks. That's really cool. I'm hearing more and more even startups doing federated learning, and so I could see why that's a big thing. That's really cool. And I've wondered about that before. Okay. So we talked about the ghost clipping. Again, not going to go into too much detail about it. They also have a way of doing the same thing for the Hessian, although it requires a second backward pass. And so after we're all said and done, the short version of this is like, they have 2 methods they're proposing. First order in-run data Shapley and second order in-run data Shapley. For both of them, you have to add points to your batch, which are your validation points, if you want to calculate these scores. But you only have to do a single backward pass for first order data Shapley, and a second, only 2 backward passes. So for first order, the only increase in training time is like increasing the size of your batch and calculating doing the forward and backward pass for those additional points. And then for second order, you have to do you have that, plus you have to do a second forward pass. So here's an example of like the runtime evaluation of these different methods. Okay. So in experiments, we'll go to table 1. If you were to train, like in the LLMs that they're training, one of the LLMs that they're training, the throughput is like it processes 76 data points per second. With first order Shapley, it's only 70 data points per second. With second order, when they're using ghost clipping, for second order Shapley, it's 34 points per second. So that's like a little less than half of that. And then when you're not using the ghost clipping, it gets way, way smaller. So 4 points per second or 2 points per second. So you can see that with the first order approach, your throughput is is really not hurt that much. One interesting thing is like all the cool results use the second order. So I was a little bit surprised that they, yeah, I was surprised they didn't show results for the first order method when they're showing all the cool results. But what this is showing you here in the results is that like the method that they've created is at least the first order one, it really doesn't hurt performance that much. Then the second thing they do is they need to check like how good the approximation is that they're using to calculate the Shapley scores. So they take the first order approximation and then they use Monte Carlo estimation, because like the true Shapley scores, I think they're like really, really expensive to compute, like prohibitively expensive. So they use Monte Carlo estimation again, but with like a very large number of samples, like 1,000 samples, they say here. And then they compare the let me zoom in so you can see, they compare the difference. So like the points show you like the Monte Carlo estimate versus the first order approximation. And you can see it's really, ideally they'd be on the same line, and you're assuming that the Monte Carlo estimation is correct. But you can see that like they're very close. So it's showing that we can assume that this method of approximating the Shapley scores is relatively accurate. Like the root mean square error is of the order 1 to the -4. So that's the second result. The third result is where they use the second order method in order to identify points that have a negative score. And they find that 16% of the data set, this pile data set, which is used to train LLMs, has a negative score. And then what they do is, so they have to train the model once to do that. But then what they do is they reduce the, they remove those data points from the data set, and they find that they get the same test loss as the original training run in like 75% of the time. So they reduce it by 25%. And they also, if they train it for the same length of time, get an increase in performance. So I thought that was a really cool result. They're using really small LLMs, and they're only doing all of this training on a single GPU, a single A100, which I think is very admirable because it makes it the results very repeatable. Although I think it would be sick to see this on like a larger data set, to be honest. Okay, so so they show, okay, we can use this to remove harmful data points if we want. Cool result. The next thing they do is that they, let's look here because it's, let's look here. Okay, so the first thing that they do is that, the next thing that they do is they use this method to actually do data attribution over time. So this is the number of steps, and then this is like the amount of space taken up by a color is like how important that data is for at that point in the training time. So at the beginning, you can see most of the data sets, this very large set of data sets, and this is, they're training a model, and then they're using it to do some math. So it's, the size of each data set is quite large, and then as you move forward, some start to dominate over others, and some almost completely disappear. So you can see that like Wikipedia, is this Wikipedia? Oh no, this is Archive. Archive has like a really big impact, and then also DM Mathematics and some other ones. But that's interesting because it shows, well, the point that they make here is that at the beginning of training a data model, I mean an LLM from scratch, all the different data is valuable or more valuable because you're just learning some basic patterns. But as you go on for a specific task, different data sets that have like more useful information in it, like Archive, which is mainly STEM papers, are more useful for math. So that's what this is showing by the fact that like, yeah.
Does it? I mean, that sort of depends on what loss metric is used for evaluating on the validation set, right? So for any say if we want to calculate the accuracy of a particular question we have to the data set, rather than anything that has been used in training, that would be completely lost, right? Because we wouldn't store the original loss gradients, yeah, for any particular question. So while maybe a data point could be not very helpful in reducing the loss as used per training on any particular piece of knowledge that the model is able to regurgitate, we can't probably say whether there is any attribution. No.
Yeah. So my interpretation of what you said is that like all of these results are specific to a specific task or even like a specific set of data points. You can't really use them for others. Is that what you're saying?
Yeah, essentially, I think it's like the question of copyright, right? So when they say that, I don't know, they train the model, and how do they train the model? Typically via some form of yeah, input, like hole filling ability of that model, right? So fill a sentence with a word or so. Now the saving of knowledge is a byproduct of that. Right? Now that is never really tested as part of the SHAP methodology, right? So any particular piece of knowledge might or might not be stored independent of whether the train loss is going up or down by that particular data point. No. So if I don't know if our validation set would contain only Dickens quotes, how well they get reproduced, we don't know whether there's any Shakespeare in there, yes or no. And while Shakespeare data points might have a low SHAP value, might have a high SHAP value because they're overall good at improving the language capability of the model. Overall, we wouldn't be able to tell whether it can reproduce Shakespeare or not, or whether there's any particular or after the fact, we can't after the fact test how yeah, whether Shakespeare has a Shakespeare corpus has any particular relevance to copyright. I didn't put it properly, but
let me tell you about the next experiment, because I would be interested to hear your thoughts on it, because it kind of it tries to tackle this issue.
Okay.
So yeah, this method, it's showing you they're testing the model on a mathematics data set, and they're showing you the value of different data sets that they train on for that. And then the last experiment, right? Is that the last one? Yeah, that's the last one. Okay, is this is the one where they're talking about like the importance of a data point for specific. Well, let me just explain the experiment, because I think it's a little bit hard for me to just generalize it. So what they do is they take a data point in their training set and they ask an LLM to paraphrase it. The first one is the prompt like that they use is paraphrase partial exactly the same. So like make it pretty much the exact same as the original one. Then the second one is paraphrase. So it's like you can't use the same words, but you want to describe the same thing. So they're taking a training point. And then they have what they call like significant paraphrase, which is when the data point should be substantially different, but hopefully it has the same ideas. And then the last one is like, give me a data point, give me a paraphrase that's a similar topic to this, but not the same. They use GTP4 to do these transformations. And then they calculate the Shapley score of over about like 32,000 data points. And then they rank the training points based on how, like their Shapley score with respect to this transformed version of that training point. So for the first two, in all the methods, you can see that you can see that the original training point has a score of 1 for all the methods, even the baselines. For the significant paraphrase, you can see that it has its rank is 32. So sorry, for the first two, it's the rank is 1. So that means that, like, of all the data points, the Shapley score says this one is the most important. And then for the significant paraphrase, its rank is 32, which means that it's like pretty high still. And then for the similar topic, then you can see that the rank is 145, 140. And then for this like baseline that they're using, you can see it's like 20,000. So it's nowhere near. But so what they argue here is that because the rank is still relatively high for similar topic, that means that these data points that are on a related topic are actually more valuable than we would think. And so we need to like if their point is like right now OpenAI is being sued by the New York Times, and they're being sued because they argue that ChatGPT has been trained on data that is almost exactly the same. It's like a paraphrase of data from the New York Times. But they're arguing here that because of these results, that even if you're using a data source that is not, and you're not, if you're using a data source that's, like if you're using a data source to generate synthetic data on the same topic and then you're training, then you're still using that data source, and it's still important and valuable. So they're trying to like argue that you can expand what is considered copyright. So when you're creating synthetic data to train an LLM off of other data. Yeah, I don't know. But anyway, that's the last point. And that was something I found interesting. I wanted to ask you all about what you think about this whole idea. It says, even when the output does not closely resemble the original copyright material, or when the model does not applies output filters to avoid generating verbatim replicates, but there's still a copyright infringement. What do you think? Or doing?
So I dealt with a company that dealt with this, was using it in the other way around. So it wanted news articles that were very similar to each other. And the metric that you showed, it's very hard to get something that acts like that. You make things a little bit different. Humans will say they're still very much the same, and all the metrics fall apart. So having something that doesn't collapse like that would be marvelous in that situation. And I know about derived works in things like Reuters. So this is financial prices. The bank got their price in, manipulate it and sell it and give that to our customers. And just the derivedness of that, it's huge legal arguments around it, and the amount of money is huge. So also the news. So yes, just underline what you said. Just yes.
Well, that's crazy. I wonder if they're going to do a startup to like help lawyers with their copyright cases.
Well, if they don't, like, it wouldn't be hard to do one on the back of this.
Yeah, I guess so. Then your retort would be like, you trained your own model to figure these out because we didn't calculate that when we trained our model. So how do you know that it's the same? But anyway, we'll have to see how this progresses. I thought it was interesting that this was one of the main things that they talked about in this paper. Maybe because it's like a very concrete use case. Now that you've said that, I can see like how valuable it would be if you don't really have a lot of methods that do this kind of thing.
There are not. Like, yeah. That the similarity of two paragraphs, it's very hard to get that.
Okay. And then just as a last thing, they talk about extensions to this method. So it seems like all their math doesn't work when you're not doing SGD. So if you're using Atom or similar optimizers, then the Ghost family techniques, you need to do something. They haven't been developed yet. They point out that one potential limitation is that you need a validation set to calculate Shapley scores. And then they argue that you need this does increase the memory constraints of your method, so that might be an issue, that you need like more memory to be able to do what they're proposing. Anyway, that's the paper. I'm sorry I wasn't able to give a great explanation of all the math, but I hope you guys took away something from it, and I'm happy to, if there's any questions, to talk about them now.
This was really good. Thank you.
Yeah, thank you very much. Great stuff.
Mm.
Cool. Well, if there's no questions, we'll end now. No paper club next week, but the week after, I think I'm doing a presentation on the dynamics of training an LLM, which is it's about a similar topic, and it's going to be super cool. Anyway, everyone have a good weekend, and see you soon.
You too.
Bye.
Thank you.
Cheers, Peter. Bye.